Okay, moving forward, we'll develop our calculus equations for each of those things that we just saw. We'll figure out my, mx, and m, all involving integrals. Okay, so let's start by defining a planar lamina. A planar lamina is a thin plate of constant density. So the truth is, a planar lamina is just they don't actually exist in the real world. They're just like thoughts, kind of like any kind of a shape. So think of a planar lamina as an infinitely thin little plate, and it might be natural. Think of it as a very, very thin like plate of metal, kind of like what we saw with fluid force. Okay, so here I've got a drawing of what might be a planar lamina. So this one is defined by two functions, f of x and g of x, and we'll say it begins at a and ends at b. If you're wondering what this dot is, that just happens to be a spot of ink on my paper, so that's nothing. So planar laminas could take any shape, and typically we'll work with things that are curved. Okay. So let's develop integral formulas for all of the pieces that we'll need to get the center of mass. So first thing we should notice is the total mass. Now we're thinking of this, it's a region, right? It's two-dimensional, but imagine it's got a density. Okay. Actually, what we say for a planar lamina, let's make that more clear, constant density. So there's the same amount of density at each location on the plate. So total mass is the density times the area. And well, all right, we can get that with an integral. Density we represent by rho. And the area of our planar lamina, well, we know from Calc 1 that we'll take the integral from a to b. And inside there, we'll take the top function minus the bottom function, f of x minus g of x. That integral would give us the area of our plate, of our planar lamina. So there you are. So there's total mass. What if we wanted the moment about the y-axis? Okay, that's my. And well, we just do a small adjustment to our mass integral. Turns out we just need to place an x right here. Why is that? Let's go back all the way to the one-dimensional case. I'll explain why. So think about total mass versus moment about the origin. So the total mass, you would just add the masses, right? m1 plus m2 plus m3. To get the moment about the origin, multiply each of those masses by x. It's distance, right? Well, that's exactly what we are doing here when we multiply an x. Right there. So we're thinking, okay, what is the mass at any given x value, right? And then we'll multiply that by its distance from the y-axis. Now in this case, it's not a point. We're almost thinking of the mass as like an entire line. All right, F minus G. But that whole thing is a certain distance away. Every point on that line is the same distance away, in fact. Okay, so if all we do is multiply the x there, then it fits our previous ways of going about it, and it's going to calculate exactly what we want. And of course, the integral adds up all of those. It does the addition. What we saw there in that one-dimensional case as well. Okay. How about the moment about the x? Okay, now here we get, it starts off in a familiar way, but we get a little bit more we've got to think about. The moment about the x-axis. Okay, so you could say, well, if we're thinking about vertical rotation, right, about the x-axis, then where we multiplied by x here, we should multiply by y. And that's exactly how we did it in the two-dimensional case. However, we're integrating with respect to x, so we can't leave the y right there. Right? We need it in terms of x. So there's a clever way to get around that. What we're going to do is think, okay, so looking back here at our graph, you know, we're thinking, okay, any given line like this might spin about the y-axis. Okay. But the y tells us the distance from the y-axis. And you think, well, but different points on this line are different distances away, which was not the case for the x, right? All of the points on that line are the same distance this way, but obviously they're different here. So the way we get around it is we say, well, okay, but because this is a planar lamina, because this has constant density, the points up here are the same mass as the points down here. So what we can get away with is say, just imagine all of the mass on that line as right in the center. Just take all those points and think of them as being right in the middle, because the points down here that are closer are going to balance out with the points up here that are further. And so if we place all of that right in the middle and think just about that one location spinning around, it's going to calculate exactly what we want. So here's what we'll do. We'll think of y as the average of f and g. F of x plus g of x over 2. So wherever we're located, just think, okay, if I want to know where the middle is, take f, take g, find the average right there in the center. So here's our formula when we're all said and done for mx. The moment about the x-axis equals, it's over 2, so we're going to like pull that outside. Think of it as rho over 2. Integral from a to b, and then we've got f of x plus g of x times f of x minus g of x dx. Now some people might think, hey, could we simplify this even further? Because isn't this like the result of difference of squares? Couldn't we do f of x squared minus g of x squared instead of having these two parts? You certainly could, and that would get you the same answer. However, I think the algebra would be easier in this style. If we just add the two functions, subtract the two functions, and then multiply, that will usually be easier than taking the difference of the squares. Although it would get you this to the same place. Okay, once we have our moments and our total mass, then we'll go about calculating the center of mass in exactly the same way we did in the two-dimensional case. So we'll call it x bar, y bar. X bar is my over the total mass m, and y bar is mx over the total mass m. Let's go for our example. It says find mx, my, and x bar, y bar for the planar lamina of density rho. And you see some functions right there as well. Okay, so first thing I'd like to point out, in a lot of problems you'll see, I don't know if it's all of them, it might be all of them in the homework. It's going to be very common for them to just say the density of your planar lamina is rho. They're not going to give you a number. There's a good reason for that. We're going to see it as we do the problem. And here, well, they give you two curves, two functions. So we're going to think it's the planar lamina that is bound between the two curves. So what you might do to get started is to just put those graphs right into Desmos. And so you can, have a good idea of what the graph looks like. I've gone ahead and done it by done a sketch by hand as well. So what I'd recommend you guys do when you see these problems, put those into Desmos, graph them so you get a good idea of what the graph is. And you may even want to sketch them out by hand as well. You might not need to do that in all cases. Just having the graph on your computer screen might be fine to set up your integrals. But you might want to sketch it by hand. It might make things easier. So when you sketch these, you notice that first graph, well, it's a parabola pointed down. It happens to pass through 2 here on the y-axis. Kind of does that shape. I don't believe it has a nice x-intercept. I don't think that's a pretty number. But then when you graph your line, well, that also goes through 2 on the y-axis, kind of angling up. And you should be able to see pretty clearly on a computerized graph that they both they intersect here at x equals 3. If that wasn't obvious that they intersected x equals 3, well, you could always do it the old-fashioned way and set the 2 equations equal to each other and solve for x. That wouldn't take too long here, and it would actually produce both x values if you did that at 0 and at 3 if you were to solve those equal to each other. But if you can tell that from the graph and you don't do any work to figure out that this is 3, perfectly okay with me if it's all visual. And in these sort of problems, these are the kind of problems that using Desmos when it comes to a quiz or a test, that's going to be perfectly okay, and it will say so in the instructions on that problem. Okay, so let's pick it up from here. We want to find, let's begin with the total mass M. All right, I'm just going to push it down a little bit. Okay, so how do we go about finding M here? Well, it's as simple as finding the area and then multiplying by rho out front. So our total mass is integral from 0 to 3. And remember, it's the top function minus the bottom, so don't mix them up. Negative x squared plus 4x. Negative x squared plus 4x plus 2 minus x plus 2. Okay. From there, let's simplify. I'm going to kind of scroll down here. Simplifying, not too bad. Before we do our integrals, a good idea. Negative x squared plus 3x, and the 2's cancel. And our integral, m equals rho negative 1/3 x to the third plus 3 over 2 x squared from 0 to 3. And then plugging in our numbers, m equals rho, plugging in the 3, you'll get 9 over 2. Subtract, plug in the 0, and well, that's a nice 0. And so our total mass here is 9 over 2 rho. Okay, moving on. We've got the total mass. Let's find the moment about the y-axis, my. So very similar. It's a good idea to do the total mass first for what you're going to see here. So remember, it's x times the difference of the two functions. So what's kind of nice about doing the total mass first, we've already simplified the difference of the two functions. So I've just put that simplified version in here. So we've got rho integral from 0 to 3, x times that difference, negative x squared plus 3x. And all right, well, This integral is not going to be too bad, just a polynomial if we multiply that out. Negative x to the third plus 3x squared. And integrating, no problem, my rho negative 1/4 x to the fourth plus, and well, there you go, x to the third from 0 to 3. And then cleaning that up, turns out when you plug in the 3, you get 27 over 4. Plugging in the 0, of course, 0. So my is 27 over 4 rho. We're almost there. We just need to do mx. mx. Okay, so our formula is rho over 2. Still integral from 0 to 3. That integral, that's going to be the same for all my, and mx. So integral still from 0 to 3. And now what is this? So this is where we add the two functions together. And we multiply that by the difference of the functions. So when we add those two functions, we've got negative x squared plus 5x plus 4. And same thing when we subtract them, negative x squared plus 3x. And well, to continue this, well, there's no easy way around it. We just got to multiply it all together. So I went ahead, multiplied them out, and simplified. All right, we've got positive x to the fourth. And then, okay, you can kind of see, where the rest of these come from. I won't go into any detail there. Rho over 2, integral 0 to 3, x to the fourth minus 8x to the third plus 11x squared plus 12x dx. And again, this is nice. We've just got this polynomial. So a nice, easy, gentle antiderivative. Negative 1/5 x to the fifth minus 2x to the fourth plus 11 over 3 x to the third plus 6x squared from 0 to 3. And it turns out plugging in 3 in this case gives you 198 over 5. Plugging in 0, of course, is 0. And we've got rho over 2 out in front. So mx works out to be 99 over 5 rho. Okay, now we found m, we found my, we found mx. Let's finish this off. And I'll just show you the rest of my work here. X bar, remember it's the opposite, it's my over m. And here's even why we can just use density rho and why you see that a lot. Because my is 27 over 4 rho. M, if you recall, was 9 over 2 rho. And so those rho's are going to cancel out, and we just got to simplify our fractions. In this case, it works out to be 3 over 2. Y bar is mx over m, and so that's the 99 over 5 rho. Over again, the m was 9 over 2 rho. The rho's cancel out, and here we end up with 22 over 5. And so we see our center of mass for this planar lamina is 3 over 2, comma 22 over 5. And you might even say this is kind of our final answer right there. If we go back to the drawing, 3 over 2, 22 over 5, it'd be kind of nice, if we were in class together and we had Desmos up, but you can graph that 1 point. Well, 3 over 2 is actually exactly halfway, right? 22 over 5, I'm not exactly sure. I think it's a little bit closer to the bottom half, right? There's more mass down here than there is up there. So it's kind of maybe kind of down there someplace. And so, if you were to have an object of this shape, then, if you were to like throw it through the air, it would spin around that center of mass. It would kind of, rotate whichever way it's spinning. And there we are. We got it. One last thing I wanted to point out. You'll see problems that ask you to find a centroid. So you'll see problems that say find the center of mass, and you'll see other problems that say find the centroid. They're the same thing. There's a small nuance difference. So we find the center of mass of a planar lamina, which has that uniform constant density. A centroid is when you're thinking it's simply an area. So if you're not thinking of it as it having a density, then you would go through all the same steps, but you would think of your answer as a centroid, as opposed to a center of mass. And so we should point that out. Also, I don't know if you guys heard me several minutes back. I was kind of explaining at some point, and I winced, and I kind of took a couple seconds. I was quiet for a couple seconds. So it turns out a bee stung my ankle while I was doing this video. And I looked down and I saw this bee like flapping around on my ankle, and I wiped it away. So there you go, working from home. Sometimes you get stung by a bee while you're lecturing. So that's a new one. All right, anyway, that's the end of 8.3.